Hello, everyone. Welcome to ECE Colloquium. It gives me great pleasure to introduce today's speaker, Professor Alex Gaeta from Columbia University. Professor Gaeta is a David Rickey professor at Columbia since 2015. Before that, he was a faculty of applied and engineering physics at Cornell for 23 years. Over the years, he has published more than 200 papers. He is also a co-founder of a startup company, right? Pico-Luz Incorporated, and he's also the founding editor-in-chief of the flagship journal Optica of Optical Society of America. He has received many awards. Most recent ones are Thomson Reuters Highly Cited Researcher and the 2019 Charles Towns Medal from Optical Society of America. He's a fellow of OIC, APS, and IEEE. Without further ado, I'd like to hear his talk on quantum photonics in the frequency domain.
Thanks, Mo. So it's a pleasure to be here. As I told Mo the last time I was here at University of Washington, it was for a SIAM meeting, which is the Society for Industrial and Applied Math. So I'm getting closer actually now to my research, now being in EE. And so certainly it's a pleasure to come here and talk to you about quantum photonics. It's great that University of Washington is really trying to establish this quantum information technology, quantum information science area, and hopefully this will give you some of the idea of the work that we're doing at Columbia, as Columbia University is also trying to establish quantum information, so we share that. The basis for a lot of quantum information ideas and a lot of the technology that's coming out of that is something called entanglement. And so what I'd like to show you is one type of entanglement, and it's probably the most standard way of doing quantum entanglement using photonics or using light. And it consists of it's a very simple device in some sense. You start off with a single photon here, and then you introduce what's called a beam splitter. And a beam splitter is just what you think. It's something that takes a beam, and maybe half of it, the light goes one way, the other half goes in the other way. And so in this case, the photon, it's coming into this beam splitter, and there's a 50% possibility it can go up this way, 50% possibility it goes up that way. And if you write the state of the system, or this photon, after it's passed through this beam splitter here, it actually forms this entangled state. So it's what's called a superposition state. And so the output is that the photon could be, for example, in this arm of the beam splitter and not in this arm, or the other way around. And it's a superposition state, and this is known as an entangled state. It is the basis for almost all of the type of quantum entanglement experiments that are currently being done. So it's very simple. It's done using a beam splitter. And of course, this beam splitter, as I've drawn it here, looks like it's just like maybe you could imagine it being a partially silvered mirror or something like that. In the very early experiments, when they generated these type of entangled states, that's precisely what they would use. I think I'm going to not use that. So very recently, there was an article. This came out a little over a year ago. This is a group from Bristol. And it's a group that is trying to build a quantum computer based on photonics. So you've maybe heard of the different types of quantum computers that exist using superconducting qubits that Google, IBM, other companies are doing. This company, which was established by Jeremy O'Brien and Mark Thompson, what they're trying to do is build a quantum computer based on photonics. And I'll talk about this a lot. And there's, of course, many components to building such a computer, but one of them is doing what's called large-scale integrated optics. So it's trying to take what has been done in electronics and applying some of those ideas, and certainly applying a lot of that technology that is being already done in electronics, all the nanofabrication technology, but applying it for photonic devices, and in terms of routing, in terms of switching, and taking all those ideas here. So this is a picture of what the actual chip looks like. This was a part of this chip. And it consists of, looking at it here, it's hard to tell what each of those devices do, but this is kind of what would be what the CAD for the chip is here. And so what you do is you actually have what's called a pump source that comes in here. It gets split many, many times. And then you have these different components here. And this part here is something called photon generation. So again, as I started off when I showed you that quantum entanglement, I showed you a photon. It is still remains relatively non-trivial to produce a single photon. It sounds like it should be trivial, but it's not so easy to do. And when I mean a single photon, not that on average you have a single photon, but that you push a button or you switch and you know for sure that you have a single photon. That turns out to be a non-trivial thing and still remains one of the big challenges. Nevertheless, you have a part here which is generating all these single photons. And then what you have to do is you have to do a whole bunch of measurements on there and actually what's called entangle all these photons, mix them all together. So here what you have are all these photons, you have detectors here, and then you have a part that is doing all the entanglement. So the beam splitters you can think of, but these are all done on an integrated device here, are all at this location here. And so this is just a simple part of this computer, but it turns out all this is in the spatial domain. So this looks like a chip. This actually looks like a chip. And when you think about entanglement, we always think about entanglement that is in the spatial domain. And I would say the community, when we think about photonics, we are always entangling photons in the spatial domain. The heart of my talk is going to be thinking in a different type of domain, which is the frequency domain. And you think, well, geez, people do photonics with different frequencies. But what I want to show you is that it is possible to actually do many of the things that are done in the spatial domain, but to do them in the frequency domain. And so the heart of my talk is thinking about how one could actually try to do photonics in the frequency domain and perform many of the operations, generate photons, but thinking about it all in the frequency domain. You'd say, well, why would you do that? Well, the spatial domain, as you imagine, as these things scale up, they get bigger. And as they get bigger, things like losses become more important, and it becomes harder to do. And actually, I would say right now, the biggest limitation right now in trying to scale up to very large systems that could be useful for quantum computation and so on, is the fact that you have losses in your system as they scale up, and those losses prevent you from actually doing the processing, computing processing that you would like to do. So what I'm going to show you here, a lot of it is based on something, and I'll talk about this more in a second, but it's based on a device, which, as I'll show you in a second, is a beam splitter, but in the frequency domain. So this is very different from probably what you're thinking about, but what it consists of, and I'll go through this, is a material. It's a standard material. In fact, it can be silicon, just like the material that you saw from the previous slide. It can be a material like silicon nitride or silicon. And what we do is we take two laser fields and we just pump it. And it turns out that this type of device, of course there's more to it, but if you design it right, can form what's called a frequency splitter, beam splitter. And what do I mean by that? Is when I come in with a single photon, that photon, there's a 50% chance that it'll keep its color, let's say red. But there's a 50% chance it'll convert to a new color, blue. And that forms our frequency beam splitter. And it is just like the spatial beam splitter. It has all the same properties. In fact, you can write this entangled state here in just the same way, but now we're in the frequency domain. And you say, well, why do it in the frequency domain? The nice thing about the frequency domain is we can scale up in frequency. It's actually very easy to do in optics. It's one of the great things about photonics. It's why telecommunications exists. You can run a lot of things in parallel in the frequency domain. All our telecommunications is done over many different frequency channels, and we can do that very easily in photonics. But the nice thing about it is, as you're scaling up in frequency, you're not taking up more space. Your losses aren't necessarily increasing. In fact, it might be, everything could still be the same device. All you're doing is just scaling up and sending more frequency channels, but your device is not getting bigger. And so this type of device has a big advantage, is that the losses don't scale in the same way as they do in the spatial domain. So I'm going to tell you how this type of device works, and I'm going to show you some of the different properties of such a device, how what one can do with that device. So the whole heart of everything that I'm doing, and as you saw, I start off with a red frequency and I'm generating a blue frequency. And my research for the last 30 years or so has centered on what's called nonlinear photonics. And certainly I remember my parents always asking me, who were not scientists, they would ask me, what are you working on? What did you do for your PhD? And I would say nonlinear photonics. And that just went over like a lead balloon. Okay. And so I imagine maybe some of you aren't even familiar with what is nonlinear photonics. And it's actually taken me, only in the last kind of 10 years have I started renaming nonlinear photonics. It's the generation of new frequencies. And that's what it boils down to. So when you think about light in conventional light that you work with, let's say sunlight passes through a window, the UV light is going to get absorbed. But you're not going to generate new frequencies. In other words, if you start off with red light coming from the sun or yellow light, it's not like all of a sudden you produce green light. It doesn't work that way. And that would be called linear photonics. Okay, you have absorption, you have index of refraction, very simple. But in nonlinear photonics, which is this whole field that's been around now for about 50 years, is the fact that we can start off with one color and we can actually generate new colors. And that's the whole heart of everything we're doing. And the basis for it is a pretty simple model that you can understand. You don't even have to go through quantum mechanics or anything, but you just start off with a very simple model, which is this toy model, which works much better than it should, model for an atom or a molecule, which is you have a nucleus, and then you have an electron that's bound to that nucleus through a spring. And you'd say, boy, how is that ever going to work? How does electron? But it works remarkably well. And it's able to predict many different aspects of how light interacts with matter. And so normally, since this is a spring here, you assume that this electron is bound through a restoring force. And normally, we think about a restoring force, we use what's called Hooke's law, which is something you learn kind of in freshman physics, which is just that the restoring force is linearly proportional to the displacement of the electron from this nucleus. And another way of thinking about it is that this electron is sitting in a parabolic potential. So you just integrate this restoring force to get what the potential is, and this integral of x becomes x squared, and so you get a parabolic potential. So that's just kind of the standard stuff. 99% of all electrodynamics textbooks, that's where they start from. They use this model, it works really well, and they never talk anything more about any corrections to this restoring force. But if you've ever fooled around with a spring or anything like that, the minute you start pulling the spring a little bit too much, you're going to actually get a nonlinear correction to that restoring force. And the way we do it is, how we always do corrections, we do a Taylor series expansion. Okay, so you say, well, this restoring force, let's add some additional terms here, correcting terms. So a quadratic term, cubic term, and so on. Okay, and so the real potential might actually look something like this. And this actually starts looking like a real atomic potential. So I'll talk about the implication of that. So from this electron, once it's displaced from the nucleus, you have what's called a dipole moment. And this is actually the source of all electromagnetic radiation. It's the fact that the electron is moving back and forth, it produces this dipole moment, and it radiates light. Then you take a whole collection of these and you get what's called a macroscopic dipole moment, and that's known as the polarization, macroscopic polarization. So it turns out if you go through all the math, we're not going to do that here, but if you go through all the math, what you'll find is that this linear part here, this is the standard one, it's all electrodynamics textbooks, you get a macroscopic dipole moment or polarization that's linearly proportional to the applied electric field. And so the end result is this proportionality constant is called the susceptibility. All the textbooks say susceptibility. I'm going to call it the linear susceptibility because that's where the nonlinear and linear are distinguished. And so this is the standard part, and again, all textbooks stop there. But it turns out that if you had included these other terms, what you'd find is, sure enough, this quadratic term would lead to a term that's quadratic in the electric field. The cubic term would lead to a term that's cubic. And so the nonlinear optics, why it's called nonlinear optics, is the fact that this macroscopic polarization depends in a nonlinear way on the electromagnetic field. So now you can understand why I couldn't explain all this to my parents. because you have to know at least a little bit of electrodynamics to understand that. And the nonlinearity is due to this. That's why it's called nonlinear optics. But what we'll see is that the fact that you have these quadratic and cubic terms, they end up leading to the generation of new frequencies. And for those, again, if you have a very strong applied math department here at University of Washington, they study oscillators, and what you can think of is that this is a linear oscillator, but once you include anharmonic terms, these nonlinear terms there, it turns out you'll generate new frequencies. This oscillator will start oscillating at new frequencies, and it's the same thing when you think in the optical domain where this comes from. Now, it turns out that for most materials, it's actually only a very restricted set of materials where this chi2 is non-vanishing. And another way of thinking about it is this quadratic term here leads to a cubic contribution to the potential. And the end result is that if I'm cubic, that means that plus x and minus x are different. And the only way you can get that is if you're in a material where it lacks inversion symmetry. That is, if I flip the material, it looks different. And so only in a very few restricted materials, ones that lack inversion symmetry, will chi2 be non-zero. And so for the vast majority of materials, whether it's glass, amorphous, water, anything that has inversion symmetry, cubic materials like silicon, the lowest order nonlinearity for all those materials is actually cubic. And so that turns out to be an important part. So if I have this cubic material, and that's the one that I'm going to be talking about here, I have a material that is cubic here. So imagine what happens if I now take two different laser beams. And they don't have to be lasers, but just think about two light fields that I come in together, and I cube these light fields. Okay, so I add them. So one of them is oscillating at one frequency, one at a different frequency, and I cube that. I'm going to get a lot of different terms. But one of the terms that'll show up will be like the square of this times the conjugate of this one here. That'll show up when you go through all the math. And it turns out that generates a new frequency. So when I look at that, you can think of is I take a cosine squared, I multiply it of one frequency times a cosine squared of another frequency, and I'm going to get a new frequency here which corresponds to this. And if you want to think in terms of the photon picture, and this is now where the quantum mechanics comes in, this term here corresponds to the annihilation of two pump photons, the creation of a signal photon, so actually a photon gets added here, and then the generation of a new photon, this idler photon, this one that's red. Okay? So this third order nonlinearity leads to the generation of new frequencies. I'm basically taking energy from this pump, and I'm transferring it to this signal and this idler here. And it turns out that this actually can be an amplification. It actually can behave as an amplifier, an optical amplifier, not a laser amplifier, but an optical amplifier where I actually can amplify signals. And like any amplifiers, even if I don't put any signal at all, I'll actually be generating photons like you can think of any amplifier produces noise. If you've ever done an audio amplifier, you turn up the volume all the way, you'll hear all that noise. Well, any amplifier introduces noise, and it turns out that here you're producing noise too, but it's photons, optical photons that are getting generated. So what we have from this process is that the photon energy has to add up, the two of these photons have to add up to these two. And so that tells you what the frequency, if this is a certain frequency here, that means that two of these photons, two of these frequencies, have to add up to the signal and idler. And that's just energy conservation. And it turns out if you want this process maybe to occur efficiently, you also have to have momentum conservation. And I'm not going to go too much into the details, but at least for the regime that we're working in here, that means that you need the dispersion to be zero inside the material. And that turns out to be a subtle part, but it's the fact that the refractive index of the material depends on frequency, and so that's a subtle part. I'm not going to talk too much about that, but that turns out to be also an important characteristic if you want this to really be a large effect. So, very simple things. So if you remember from that picture that I showed on that computer, I said photon generation. How are we generating photons? Okay, so here's something that you can go home Today, if you talk to your parents, I'm big on talking to your parents about what you're doing. As a parent, I always want to hear from my children, when they graduated from college or whatever, I always want to hear what they're doing, what they're looking, what courses, and they never want to tell me, okay? But here I want you to tell them this, okay? Which is, hey, I learned today how I can generate a single photon and a photon without doubt that is not 0 or 2 photons, but always 1 photon, okay? And this is how you would do it. You would take this material, Chi3 material, which actually can be glass. It can be an optical fiber. Almost any material will show this. You come in with a laser beam, and what you find is, remember I said that this is like an amplifier, and it'll produce these photons, but it turns out it produces them always in pairs. It's a very unusual type of amplifier. And the reason being is if I generate this red photon over here through this process, I have to generate a blue photon. This process cannot occur. These always have to be generated in pairs. And so the end result, since they're generated in pairs, is they're very strongly correlated at the photon level. That means if I detect a red photon or a blue photon, there must be a corresponding red and blue photon as well. So what you do is you take a photodetector, could be a photomultiplier tube, and I sit here and I wait. And once I detect a blue photon, I know with 100% certainty that there's a red photon there. And then what I can do is I could even detect it, and once I detect the blue photon, I turn this off very quickly, and I know with 100% certainty that there is a red photon traveling along that was detected that was generated at exactly the same time as this blue photon, and I know with 100-degree certainty that is a single photon, not 0, not 2, not 3, but always 1. And every time I repeat the measurement on this system, every time I do this little experiment, I will always have 1 photon. So this is one way of generating it. There's a subtle part here, which is these are noise photons, and you don't know when it comes out. So it's still not the push button version. But nevertheless, at least we can get to the point where we can generate a single photon state, we just don't know when it comes out. Yes?
What's the time scale of that? So when I detect it, how fast do I have to turn it off?
So it would depend. So this is a really important part, which is you need to be able to turn it off faster than they're being generated. And that turns out to be very important because you'd say, well, if you want to generate many of these, you just turn up the power here and I can generate many at a time. The problem is of course, then if you don't do this fast enough, you'll generate sometimes 2 photons. And of course, it'll be 2 photons. You'll definitely have 1 or 2 or 3, but that doesn't help you. If you want 1, and for many of these experiments, you want 1. If you start generating 2, it hurts your processing, quantum processing. So typically the rates, it depends how intense this is, but typically the rates are limited there to make sure that your whole system here, how it works, is always operating in such a way that you know for at least a period of time there's only 1 photon that's being generated. So, I'm not going to talk too much about this. This is just an equation indicating this, but part of this is that the relationship between this Idler field and the input, these are quantum operators. I'm not going to go into detail, but the important part is there's a relationship between the inputs of the 2 fields here, which normally are in vacuum, and then you have these Koshs and Cinches. The main part here is that these can be much, much greater than 1. And that you can think of as that this represents the amplification. These can be 1,000,000. They can be very large. And that would represent that, if I put in a signal here, it could get amplified as it goes through. And the main part there is this is not a unitary transformation. That's the only part. So now let's go back to that picture here. This is this Photonic-Chip. And if you look, this is the part where they're generating the photons here. So they're generating pairs of photons. They're in these silicon waveguides. They're little spirals here. And then what they do is you see there's a red and blue. It's hard to see there, but there's pairs that are getting generated at all these points here. And the silicon is this Chi3 material. And so then what they do is they have all these little interferometers here. And all this here is just to separate out the red and blue photons. So then they get down to the bottom here, and they have red and blue photons. And what they have to do, this shows you how hard this quantum computing is I already told you that these come out randomly. So what they have to do is wait till, let's say in this case, I don't know, that looks like there's about 20. Could you imagine you have to wait till 20 happen to be generated simultaneously at the same time? And to be honest, to really start becoming useful, they probably have to be of the order of 1 million. So you can see how hard this problem is. We're generating photons, and yeah, you could have 1 million of these, and actually this is the power of integrated photonics, but now you have to wait till 1 million are generated, all happen to be generated at exactly the same time, and most of the time it's not. And so this is a real huge challenge, but I'm just giving you a focus here on how hard it would be to do this photonic chip. But here they separate them out, and then here are all the beam splitters, and this is where all the entanglement is getting done. And so as I mentioned earlier, we have this entanglement, we have the beam splitters. They're doing these beam splitters with silicon, so this is where all that's being done. So this is just one part of building a photonic computer. There's other parts, there's detection and so on, but this is at least a part here that's being done. So now there's so I've told you about entanglement and photon generation for photonics. These are two critical aspects. Then there's a third one, which is a subtle one, but turns out to be a very important one. And it's called a quantum frequency converter. So what's a quantum frequency converter? Imagine you have my photons, I have a photonic state here, and it could be, imagine it's a single photon actually. And what it does is this frequency converter, and imagine it's a certain color, blue, and you need to be, this frequency converter, this ideal frequency converter, changes it to a new frequency, green. And you'd say, well, that doesn't sound so hard. But it needs to do it while completely preserving this quantum state. So imagine if it's a single photon here, it produces exactly a single photon here. And it needs to do it without adding any noise, okay? And so both of those things, the fact that I preserve the fidelity of the state and I add no noise, are non-trivial to do. You'd say, so why are these so useful? A number of reasons. One is sometimes there are many devices that are really good at generating single photons. A lot of work that's going on here at University of Washington and Kai Mei's group and other groups, ARCA's group here, where you're using quantum dots or using other special materials that are really good. They operate at certain wavelength regimes at generating photons. It could be at, let's say, 600 nanometers, which is visible, red. But we want to transmit these photons on optical fibers where they operate at 1500 nanometers. That's where all telecommunications takes place. So how can I transfer those photons to this new one? Well, if you have a quantum frequency converter, that's one way of doing it. A very big field now that's coming up is using superconducting microwave photons. So this is very big. So this operates in the microwave regime, which is great. You can do a lot of amazing photon processing with microwave photons in these systems. And companies like Google, they just published a paper in Nature on this of really being able to do 51 qubits, and it's amazing what can be done there. The problem is, again, is if you want to extend this over certain distances, if you want to couple many of these qubits together, it probably has to be done with optics. And so what you need to do is take these microwaves qubits, or these states that are generated there, and convert them to telecom. So that's a huge frequency change. It's not just blue to green, it's microwave to optical, and then optical back to microwave. So that's a type of frequency conversion that's important. And again, as I'll just go through, is that a key part is that you have to do this with high efficiency and ultra low noise. So these are the main reasons of why people want to do frequency conversion. And there's lots of different ways of doing it using Chi2, which I told you second order, but also Chi3. So here I'll show you one example of this nonlinearity with a Chi2 interaction, how I would change, let's say, blue to red. So what you do is you pump this system here with, let's say, a green laser. And in a Chi2 medium, this is what the picture looks like. I have a signal that I want to convert. It mixes in this Chi2 medium. Remember, it's E squared, so it's kind of like a mixing process. It mixes with this pump field here, and it turns out you'll generate this field here, which is sometimes called the Idler field. And it turns out if you go through all the math, this Idler field is just related to the signal field in this way here. And it turns out it's a sine, and I won't go through the details, but this just depends on the power of the pump, roughly speaking. So if you have a sufficiently high pump power and high nonlinearity, I can make this theta nonlinear 90 degrees, or pi over 2, so that the Idler field looks just like the signal field. And if you look at this, this actually looks a little bit like a beam splitter. It's a unitary transformation, and I can convert completely this signal field to the Idler field. Note that if I keep this theta nonlinear to be, let's say, pi over 4, this starts looking also like a sine. This would give me a 1 over square root of 2, 1 over square root of 2, and it looks like an entangled state. This actually would form this quantum frequency quantum frequency converter. If I don't do 100% conversion, but only 50%, it starts looking like a frequency beam splitter. That is, the output field here looks like part of my Idler field plus part of the signal field. And I'm going to get to that more because we're going to use chi3, and I'll explain why. So this is the chi3 system, and this is what I'm going to be talking, my whole talk is based on this interaction. So we now have a third order nonlinear interaction, so it involves one more extra field. In this case, 2 pump waves. So I come in with 2 pump waves, pump wave here, and it turns out, again, this signal here is going to be related to this Idler field here. So it turns out under the right conditions, the equation you see is identical as for the second order. And the key part here is that I can do this frequency conversion. I can make this 100%, so I can make it so that this output field here is everything like there. But I can also make it behave like this frequency beam splitter. That is that I come in with a signal field and maybe half stays in the signal and half goes to the Idler. Now, you'd say, well, why don't you use a chi2? The chi3, the beauty of it is we can do this all in silicon. We can do this in integrated geometries. All the wavelengths are pretty similar. That turns out there's real advantages there. And so that's why we have always are doing everything in chi3 materials. Now, in terms of intuition, so I've just introduced this nonlinear susceptibility. But what you can think of is that this chi3 medium, it turns out what that leads to is an index of refraction of the material that depends on intensity. Okay, so normally index of refraction we think about as constant. But it turns out it can depend on intensity. So if I bring in 2 pump waves of different frequencies, they'll actually interfere. And that interference will reflect in regions where the index of refraction is a little higher, a little lower. And that forms what's called a grating. And because they're at different frequencies, it's a grating that's moving. So this signal field comes in, it scatters off that grating, and that's what produces the Idler. So in terms of a classical description of what's actually going on in this type of quantum frequency conversion, it's pretty simple. And of course, depending on the strength of these 2 pump fields, I can get in the regime where my signal, as it travels through the material, gets completely converted, but I can also operate in this regime. And here, this is 50-50. That's the frequency beam splitter that I've been talking about. So here I'm going to tell you about 4 different types of measurements where we use this frequency beam splitter here, and how we use this frequency converter to do a number of different types of experiments that are crucial for showing that you can do this kind of quantum photonics in the frequency domain. So the first part is to get more pragmatic. How do we actually generate this type of 4-wave mixing? What does it actually look like? And in my lab, we explore, so let me talk a little bit about this. This is just, remember I mentioned the fact that you have energy conservation. You also need to match all the propagation constants. And I won't go too much into the details, but it requires some tailoring of the dispersion of the interaction. This is something my group kind of has, it's been a big part of my group, is everything we do. We are always thinking about this, but you can think of this called phase matching or conserving momentum. And it has to do with engineering the dispersion of your interaction to ensure that you can do this. The main crux of it is this is what it's going to look like. Our 2 pump fields are going to be here, and our signal and Idler field here. The separation of the pumps determines if I come in with a signal here, then that means the Idler will be generated at this frequency. And that's just to ensure that I have this energy conservation that occurs here. So we do many different types of nonlinear interactions. the one I'll be talking about here is actually, most of it is in optical fiber. This is off-the-shelf fiber sold by Corning, but Corning designs this for telecommunications, and they spend a lot of time designing it so it has the right dispersion. And it turns out for the nonlinear optics we want to do, that turns out to be perfect. It's a coincidence, but it turns out to work really well. We're currently also working a lot in these other types of platforms, which are chip-based. And again, as I told you, eventually, if you want to put many of this all integrated on a chip, you're going to have to do this. And so this is something that we've worked a lot in. And these are different types, primarily silicon nitride, which again is CMOS compatible. And here, for example, is a spiral waveguide. And so you can get, we can get lengths of 10 centimeters long interactions in a 1 millimeter squared area. So it turns out these can be really amazing devices in terms of having long interaction lengths in very small areas. And so this currently, we are working on that, but everything I'm going to tell you about here was done in optical fiber. And so as I mentioned to you, a key part is that you have noise always in this system. And we want to avoid noise as much as possible. So how do we do this? So I'm not going to go too much into the details about the Raman scattering, but there's an effect that adds noise. It's called Raman scattering. You can think of it's just the fact that the glass is vibrating. It's on a very small scale vibration, but there are lots of vibrations here. And you shine light into it, and what happens is you generate photons. They scatter off these vibrations and generate new frequencies, and it creates a lot of problems. So what we do is we take two pumps that are at this location here. This is in the telecommunications band. And we put them very far away from our signal and idler. And what that does is, remember, each of these pumps are going to be generating photon pairs. We don't want those photon pairs being generated. We just want to do simple frequency conversion. So we make sure that they're separated by a large wavelength regime. And then this red line here represents the amount of spontaneous Raman scattering we get. And it turns out at room temperature, it looks like this, which is not great because this corresponds to a lot of noise. But all you have to do is cool the fiber down to about 77 degrees Kelvin. And it turns out under those conditions, the Raman noise is almost negligible at this point. So this is the wavelengths that we're operating. So the signal and idler are going to be down in around 1200 nanometers. And the two pumps are in the telecommunications band at 1500. So that's where we're going to be doing our interaction here. And this is what the experimental setup looks like. We have the two pumps here. These are just off-the-shelf lasers, telecommunications lasers. We combine them and we send them inside the fiber. We generate our single photons in this location here. I won't go into the details how this works, but it's similar to the Chi-3 I told you about. We generate single photons, they interact here. And then what we do is we filter them and we filter and detect both the signal and the idler to see are we able to do frequency conversion and so on. And so it turns out, again, if you're operating at room temperature, it turns out that even if you don't put any signal and idler, this is the whole noise over this window here that we generate photons. And so that's not a good thing. But if you cool the fiber down, the noise goes down to the point where you essentially can ignore it. So here's a plot of the signal. That's the blue, as a function of time. So this actually represents, the pulse is actually turned on at this point, the pump pulses. And so what you see is the signal goes down, goes pretty much to zero. That's great. That means it's getting completely converted, and this is the idler. So this is the frequency conversion. We're going from the blue to the red, and this is pretty close to 100% conversion. In fact, if we match everything just right, we can get pretty much 99% conversion with no noise. So this is indicating that we can do frequency conversion incredibly high efficiency. These are the highest that have been demonstrated in any system for photonics. And we can operate close to 99%. For single photons, it operates, and I won't go into the details, but the photons their bandwidth tends to be a little bit larger. And so we're typically in the 93 to 96% regime, but this is a single photon. And you can see that it gets completely converted. And this, again, is a function of pump power. So remember, you saw that cosine squared dependence, and that shows up here. Now, there's a measurement that you can make to actually determine whether it's truly a single photon. And what it is you take a beam splitter, and you have two detectors. And what I do is I say, okay, if I look at the correlation between detecting a photon here and a photon here simultaneously. And so at 0 time delay, if it's truly one photon, you should never be able to detect a photon. And this is called, it's a very famous measurement in photonics, it's called G2, and it's this correlation. And what you want is that G2 to be very close to 0, because that indicates it's truly a single photon. You're not sometimes getting 2 photons, you're not getting 0. And so what you see here is this dip, and this dip here, this is telling you basically how long the photon is, roughly speaking. So our photons here are about a nanosecond in duration or so. And so what you see here is it's a dip. And so the signal, that's what we're putting in, that's close to there. And what you see is the converted is very close. So that indicates that we're able to do this frequency conversion. We preserve, it stays, it behaves just like a single photon. So then the next experiment that we do, again, it's another kind of test. It turns out to be a very important one, is something called the Hong-Ou-Mandel interference. So this is nice because many effects are usually named after the lead person of a group, the professor. But here, both the two students are also named on this paper, which is good. Okay, so this is a very famous effect called Hong-Ou-Mandel. They were both graduate students at Rochester when I was there. So I remember actually this experiment that they were doing. And it turns out to be a very important one to indicate kind of how good are the quality of the photons in your system and how you're able to entangle them. And so this is done in 1987, but it turns out, nowadays, if you're talking about a single photon source, you almost cannot publish a paper without doing this type of measurement. It is telling you how good a quality is. And it is one of these things that I'm still at the stage that I would not be able to explain it to my parents why it works. Because it is purely a quantum mechanical effect, but it's a very fundamental one, and it seems almost unbelievable, okay? And it's so simple. This one requires that you have 2 photons that you inject and you put them on a beam splitter. So there's 4 possible outcomes. One is that this photon gets transmitted, this gets reflected, so you end up with 2 photons here. You could imagine that this photon gets transmitted, this one gets transmitted, so I have 1 photon in each location. This one gets reflected, this gets reflected, so again I have 1 photon in each location. And then this one can get reflected and this one gets transmitted, so I end up with 2 photons here. Now, it turns out that if you go through the math, that these two actually destructively interfere. So the only possibility, assuming these are really good photons, that actually, as I'll show you, the output are good photons, the only possibility is that 2 photons come out here, 2 photons come in here. So the state that is produced is this funny entangled state where you have 2 photons in one arm, 2 in the other, but you never get 1 in 1. So again, I still don't have a good intuition. I mean, I know we always say there's quantum interference, destructive interference, but giving a 1-sentence quick description why this actually works is unbelievable. That I come in with 2 photons and I never get 1 in 1. And this only happens in the quantum regime. You have to have these 2 photons. So if you look at the coincidence counts, that is, if I put detectors here and detect whether I get if these photons are not delayed, so that's no delay, this would be 0 delay here, the probability of detecting 1 photon here and 1 photon here is 0. So this is called Hong-Ou-Mandel interference. Okay. So now let's do this in the frequency domain. So in the frequency domain, I would have a blue photon, I guess I'll call that blue, and a red photon. So in this case, I have these 2 photons. So there's, again, 4 possibilities. Imagine I operate my frequency converter so it's 50%. And so now there's a possibility that the blue photon doesn't get converted, but the red one does. So I'd have 2 blue photons. Then you could have a blue photon not get converted and the red photon not get converted. So I have 1 of each. The blue gets converted, the red gets converted, so I have 1 of each. And then I could have this get converted, but this one doesn't, so I'd have 2 red. So those are the 4 possibilities. But it turns out, again, if this is a true frequency converter, these 2 destructively interfere, and so these cancel. And so the only possible outcome is that you end up with 2 blue photons or 2 red photons. It seems unbelievable to me. Still to this day, I explain it to you. Why should that work that way? But it does, okay? And so the idea is to actually show this experimentally. So again, it turns out it's a non-trivial because we have to generate these photons, a signal and Euler photon at exactly the right frequency wavelength separation to match our 2 pumps. So it's a little bit harder here. So the way we do that is we have a silicon nitride microring, which is generating photons in pairs. So we pump it here, and I'm not gonna go through too much details, but remember I told you earlier, we have pairs of photons that are generated at this point through 4-wave mixing. And so this blue is with this yellow, this red is with this blue, this one is with this one. And so what we do is we do heralded detection, like I told you. So we detect over here, and if I detect, for example, a photon here and a photon there, that means there's a photon here and a photon here. And this frequency separation is determined by the modes of the silicon microresonator. So now I detect these photons, they're produced in pairs, and we know their wavelength separation extremely well. So I come in with 2 pumps that are separated very close to the separation here. I do my Bragg scattering 4-wave mixing, and if things are right, I should get blue photons or red photons, and nothing in between. Now, what I can do is change this separation, and what you'll see is then that destructive interference should maybe not be so good. And so that was the experiment we did. And so here shows the results. So the top one here, this is when everything is matched up perfectly. The red is if the pumps are off. So it turns out, I'm not going to go into details, but the probability of detecting a red and blue photon is given by this curve here. And this has to do more with the silicon nitride microresonator. However, if now I turn on the pumps, you see that I never generate a red and blue photon. I only generate one of each. In fact, this is what you get here. It's just flat. It's always 0. This is very interesting because this is a different way of doing Hong-Ou-Mandel interference because we actually can time resolve the photons in this case. And then as we detune them, it turns out you start getting more of these wiggles here. And it turns out you can model this very well, this behavior, and we get really good behavior. So the solid lines represent the cases in which the pumps are not matched to these, and so it turns out you get these wiggles that are shown here, and so we can actually model this and predict it very well. But this shows this Hong-Ou-Mandel interference, but now in the frequency domain in a very nice way. So the next experiment to do is what's called a Ramsey interferometer. And this you can think of as I have 2 photons here that are being generated. And what you can think of it is this represents a qubit. It's a frequency qubit where I have red and blue. And it's just like any qubit has 2 possible states. We have 2 possible states here. But the 2 states are that it could be a red photon or a blue photon. So Ramsey interference was taken from the studies of atomic and molecular systems, 2-state systems, where you had a ground state and an excited state. And it turns out what you could do is you would send in a pulse, a short pulse, so that there would be some probability of exciting the atom or molecule to this excited state. And now the atom or molecule would be in a superposition. You could then have some process occur here where the atom or molecule undergoes some kind of evolution, and then you hit it with another pulse. And it turns out that by measuring whether the atom or molecule was still in the ground state or the excited state, you could infer something about what actually happened in the system here. And this is called Ramsey interference. It's a very common way of doing kind of spectroscopy or with molecular and atomic systems. Okay. So we can do the same thing in our system, but now just using photons. Imagine that if it's a blue photon, it's in the ground state, and if it's a red photon, it's our excited state. So this is our frequency qubit. So we're doing everything in the frequency domain. And so you could do exactly the same thing. The nice thing about this is unlike an atom or molecule, there's no decay between the two. So there's actually some very interesting ideas in terms of coupling this to an optomechanical system or so on. I'm not going to go into the details about that. But we have this system where we do our frequency conversion and we put it in a coherent superposition. We allow it to undergo free evolution, which turns out to be very easy. And then what we do is we detect if it's red or blue photon. And so this Ramsey interference, it can be done here. I'm not going to go through too much of the details, but just to show that we're generating photons here. And what we do is we excite it in a superposition here. This is our nonlinear fiber. And then our free evolution is just that we pass the two photons through and have them strike a mirror and then do our interaction. So just to give you an idea, go back to the Ramsey interference here. We have two pulses that we send it. So in our case, we're going to give it, basically excite it into a coherent superposition and then hit it again. And we can get information about what happens here. And so this Ramsey interference is done here. And so again, we can see that in this case here, as we adjust the phase, we can actually see the Ramsey interference as a cosine. This is done with a single photon, and it's all done again in the frequency domain. So the last part I'm going to talk about is this kind of holy grail, which many of us in the photonic community are trying to do, which is to generate photons on demand. Remember I said that, how do you know you have exactly a single photon? And the way currently, and again, there's a lot of work that's being done at University of Washington here on using quantum dots and other types of quantum emitters to do this. But as I told you, there's also this potential for doing this photon generation using nonlinear crystals, where you generate pairs of photons, you detect one, and that heralds another one. So, as was mentioned by the question here, one of the issues that comes up is, well, if you want to do this on demand, why don't we just keep turning up the pump? And the problem is, if you keep turning up the pump, is then you'll start generating not just one photon, but two photons pairs, three photons, and so on. And so that turns out that really limits you, is you're limited in terms of how certain can you be that there's a single photon with this system that is on demand. Everything is still probabilistic. And one way of getting around that is to do what's called multiplexing. You take many of these sources all together, which are all generating photon pairs probabilistically. So I have an idler here, I can detect it. And now I have a signal. Idler here, I detect it. This one here, here. So they're all running in parallel. And so what you do is you have a whole bunch of electronic logic here, all of them waiting for a photon to be detected. And once it's detected, you turn all of them off. But the nice thing about it is all of these basically are adding up the probability together. And so if you get enough of these together, you can get basically to a point where you push a button and you can get a photon on demand. Okay. There've been a lot of different approaches that people are currently looking to do this, where they do the spatial multiplexing, again using photonic chips, time multiplexing, and then some combination. Really nice results that have been generated. But again, a real issue that comes up with all of these is that as you scale up to many of these that you're multiplexing, you know what, let me hop to that. As you scale up to many of them, what you find is you take many of these multiplex sources, the system is getting bigger and bigger, you're introducing losses, and actually what you find is if you look at the heralding probability, that is the chance that you're going to get this photon with as close to unity certainty as possible, is that actually you lose. The actual heralding probability goes down. But what we're going to do is do frequency multiplexing. So the idea is, again, is we can generate photons, all these pairs, and what we do is we do frequency conversion and always convert to the same color. And so we're generating all these photons simultaneously, but we multiplex them and then convert them all to the same color. So here I'll show you what that setup looks like. It's almost easier to look at this. So we have a crystal here. We're generating photon pairs. We detect them. And so they're all different colors. There's a green, aquamarine, blue, and all these photons are getting generated, but they're all different colors. And so what we need to do is do frequency conversion to convert them all to the same color, let's say green. So what we do is we have a bunch of different pumps, and what we do is we find out which photon was generated, what color it is by heralding here, and then we convert it. So for example, if a photon is generated here, that means it's this color. And then we don't turn on any of the pumps and we get green. If this one is generated, that means that the photon is going to be this color, so we turn on this pump and this pump, let's say this one and this one here. If this is triggered, that means we generated a blue photon, and so then we generate this pump and this one over here. And so we're always just changing the color. And no matter what, we're always shifting it to the green. And so this is a way of doing this multiplexing. So we've done these experiments, and it turns out This is what each individually gets. This is the heralding the photon count rate. And then if you bring them all together, you get about an enhancement of 3.5 dB. So we should see a full factor of 3, which would be like, I don't know, about a little over 4 dB. But we get pretty good. So 3.5 enhancement here using this frequency multiplexing. And the nice thing about, I won't go through the details, the nice thing about the system is it scales very well to doing this on chip. So eventually what we're going to do is build a microresonator where we're generating these photon pairs on chip. They're probabilistic, but then what we do is we have frequency conversion with many pumps here, and we always keep converting them here. And this system could scale very nicely onto a photonic chip. So I'll just wrap up. This work was done primarily by a group of students in my group and postdocs, but most of the work was done by a single student, which is Chitali Yoshi, who is just about to graduate, get her PhD, and join a group at Caltech. But Chitali Yoshi has really done most of the work in the group. Thanks for your attention.
Thank you, Alex. I'd just like to add this talk is also co-sponsored by QuantumX, which is a campus-wide initiative to facilitate quantum information research. Now we open for maybe 2 quick questions.
So when you talk about this frequency and not having that many components, so is the goal is like each kind of this micro ring resonator, each of the mode is going to be like get different photons? Like how is going to reduce the number of components? That part.
So this part here, you're saying?
Yeah, I'm saying like when you say like this big chip that Bristol did, ultimately how we're going to reduce the components?
So, so what I would say, for example, is we can create, so I guess a good example is we have this waveguide here. This is where we can do our nonlinear frequency conversion. So what we could do, for example, is if we want to add different beam splitters, it turns out all you need to do is, it's the same waveguide, you just add another pump wave. So this stays fixed. So in terms of spatially, so all you're adding are pumps. So of course, you can't get anything for nothing, but it's very easy to add pump waves, and the losses are fixed. So this is a key part, is that as you scale this up, you're adding more pump waves, you're putting more pumps there. Now, of course, it doesn't mean you have to design things properly to avoid, you only want certain interactions and so on. But the nice thing about it is that, you are just adding pump waves. And so, for example, you can design, which can't be so easily done in photonics. I can do an end-to-end beam splitter in one step. Because I can just have end pumps, and then I bring in end signals, and they can, depending on the strength of the pump, I can couple those end photons here all together inside this interaction. And that's something that can't be so easily done in photonics. I mean, when you look at these N-by-N switches, they're much bigger, require lots of different components. Here, it can be done in one step.
Is the idea that you use kind of frequency comb to get all those?
Yeah, so in some sense, exactly. So I mean, I didn't mention that, but we do a lot of work on frequency combs, and so generating like a comb of these is pretty straightforward, actually. You can generate, without much effort, let's say 100 or maybe even 1,000 of these pumps, all perfectly spaced. And so I think the scaling at least looks pretty promising there. Now, whether you can get to 1 million, that's another story, but I think I can argue the case you can get to 1 million here a little more easily than you can in the other system.
So I guess the unique advantage is you can utilize frequency division multiplexing to save space. And so suppose you want to generate many photons of different frequencies, not just red and blue. What's the smallest frequency spacing you think you can achieve, and how many channels you think you can get?
So everything we did here, the spacing was probably about 5 nanometers, which is pretty big. We can generate these frequency combs on, on a grid that could be 50 gigahertz, maybe even down to 20 gigahertz spacing. So that starts getting pretty small. And there has been recent work, which the problem is, of course, is you want to make sure that if you can generate on a grid, which can be done in a number of ways, then you can easily separate it out. And so, I mean, it's possible to generate frequency combs using electro-optic modulators where you could make the spacing at gigahertz, so you could make it really narrow. The problem is how you demultiplex and get each of those channels out. So it's actually very easy to create kind of a frequency grid using electro-optic modulators. It's not so easy always to demultiplex and get those photons out. But I would say the spacing is almost whatever you want it to be. Certainly, just for experimental convenience, ours, it was relatively large. But you know, certainly without much effort, just using current things in the lab, we could easily keep this down at the tens of gigahertz spacing.
Okay, we just run out of time. Let's thank the speaker again.